So today we're going to be talking about matrix operations. So in matrix operations, first we need to decide what is a matrix. So a matrix, we're not talking about the concept from the movie released in the 90s. Instead, we're talking about an array of numbers, just like this one, enclosed within square brackets, denoted by a capital letter, having a size of mn. Mn means rows, so we have m rows and n columns. So we always use rows by columns as our notation. So these matrices can hold any kind of data. So for the purposes of solving linear systems, what this whole class is about, we're going to be mainly dealing with scalars like integers and fractions and decimals. So we can actually index all of these based on subscripts of what row and column they're in. So you'll see that this first entry is in the first row, first column. So by rows, I mean the horizontal lines, just like this. And then by columns, I mean the vertical ones. Just kind of like in architecture, you have like columns outside of fancy houses. So these are the columns here. So now, let's see what we can do with matrices and look at some examples of them. The first example here at the very top is A, and that is a 2 by 3 matrix because it has 2 rows and 3 columns. So see the 2 rows, 1, 2, and the 3 columns, 1, 2, 3. Similarly, B is also a 2 by 3 matrix. C here is a 1, 2, 3 rows by 1, 2 columns, so 3 by 2 matrix. Okay, now if we look at D, you might be like, hey, wow, that looks more like a vector. Which actually, it's kind of cool that it also is, but it's also a 1 by 3 matrix. So just like all integers are real numbers, but not all real numbers are integers, all vectors are matrices, but not all matrices are vectors. And then lastly, our last example here is E, and this just says it's a 2 by 2 matrix, you know, so it means it has 2 rows and 2 columns, which is a special case of a matrix, and that is called a square matrix. So in a square matrix, we have the same number of rows as columns, just like in a square in geometry, we have the same length of each side. So that's kind of cool. A couple examples of matrices. What can we do with these? So we can do matrix addition and subtraction. So let's look here first at addition. So if we want to add A and B, we're just adding A and B here, then we're going to have this. It's going to be component-wise or element-wise. So each element in the corresponding matrix is going to be added, but only if they have the same index like we talked about up here. So basically, if they're in the same position, they get added together. So let's see this in action. Okay, so we have just added together A and B. So you'll notice, like I was saying, it's element-wise. So we're adding each element in the corresponding position of the next matrix. So, for example, we have our first entry of A in the first row, first column. So we're going to add it to the entry in the first row, first column of B. So we see there, 1 plus 2. And then we're going to take our first row, second column, and add it to the first row, second column entry, -1 plus 3, right there. And then our third entry, first row, third entry, first row, 3 plus -4. We do the same thing, 5 plus 6, 2 plus 7, -2 plus -1, right there. And then all we have to do is simplify, and then we end up with this matrix here of A plus B. So, if you remember, back in the olden days, we had this word that we first learned about in maybe middle school called commutative. This is a special property of different operations that means that A plus B equals B plus A. So in binary operations, we always kind of want to think like, hey, is it commutative? So for matrix addition, it is commutative because we're not messing with the rows or columns. We're just adding element-wise. Scalar addition is commutative, so is matrix addition. However, if we consider matrix subtraction, we have something a little different. So all we have to do, though, is subtract. So we just change the sign here, and then we'll just change all of these signs, and we have a new matrix. So then after we subtract B from A, we're left with this matrix. So addition here was commutative. Subtraction, not so much, because scalar subtraction isn't commutative, so neither is matrix subtraction. So what did you notice about the dimensions that we need when we add and subtract these two matrices? For both matrix addition and subtraction, we need the same dimensions. This is super important because let's say we had another column here on A, but not on B. So if we got over to whatever like this element here would be, we would have nothing to add it to here on B. So it's not defined. So for matrix addition and subtraction, you always want to have the same dimensions. This is a binary operation, matrix addition and subtraction, which means that we have two different elements that we are adding together or subtracting. So this is binary. So let's look at an example of a matrix operation that is unary, which means you only need one term. So for this operation, the matrix transpose, or transpose for short, it is a, like I said before, a unary operation. So we only need one term to deal with. So with the unary operation, we just consider one matrix, and with the transpose, we're going to be considering that matrix and then swapping all the rows and columns. So we're going to just do a good old swap-a-rooney with our rows and columns. So if we kind of look at this with an abstract example here, if we take M, we want to take the transpose of it. We denote the transpose with a capital T as the superscript. And like I said, we're going to do a swap-a-rooney with the rows and columns. So now we're going to have an N by M matrix, but this still means the number of rows, and M means now the number of columns. So we still have the same order that we defined them as, but just we have a different number of them. So now if we look here at M, we're going to just do a swap, like I said, with rows and columns. So this row is going to become our first column, first row becomes first column. So we now have A11, A12, all the way to A1N as our first column. Our second row is going to become our, you guessed it, second column. All the way down to A2N. And then now we bring all these out. Our last row is going to be our last column. So we have AM1, AM2, all the way to AMN. So you'll notice here that our matrix transpose just swapped all of the rows and columns. You'll see this row right here, our second row, is our second column. Our last row is our last column, and so on and so forth. So let's look at a few more concrete examples. So if we take C, and we want to take the transpose of C, what we can do is all we do is we take our original C, I'm just going to write it up here so we don't have to keep on looking up that way, and we swap all of the rows and columns. So we'll take our first row here, it's become our first column. So first of all, let's make sure we remember C is a 3 by 2 matrix, so we're going to expect a 2 by 3 matrix out here. So we're going to take our first row, make it our first column, take our second row, make it our second column, and then we're going to take our third row and make it our third column. So we're left with this 2 by 3 matrix. Now we took all of our rows and made them columns. So let's see what happens if we make each column into a row. So we're still expecting a 2 by 3 matrix because we have swapped our rows and columns. Then we're going to take our first column, make it our first row, and then we're going to take our second column and make it our second row. Okay, so now notice hey, these are the same matrices, which means that it doesn't matter if you take rows by columns or columns by rows. So now let's look at one more example. This one might seem kind of silly, but we're going to think about D. So D is 3, 1, negative 2, right? And it is a 1 by 3 matrix. So when we take the transpose, we're going to expect a 3 by 1. So even though it only has one row, that's going to be our one column in the transpose of D. Just like that. So now you have learned to master 3 different matrix operations. Stay tuned for next time. We'll get to know a little bit more about matrix multiplication.